Okay, let me start. Welcome everyone to another lecture in GR. We have now introduced a lot of mathematical ingredients, and this will actually today be one of the last lectures where I will do pure mathematics for some time. Next week, I will move to a somehow different type of discussion. Next week, we will fill this mathematics that we have seen with, in a way, physical content and study the behavior of black holes. Or more precisely, we will study how the metric of a black hole influences trajectories around the black hole, or even when you pass the event horizon of a black hole. And that will give us a lot of insight in somehow GR in general, because it is an example of a very interesting metric of space-time. And of course, it's something real. Black holes, as far as we know today, exist. But for today, we still have to continue a bit with the mathematical framework. And last time, I hope you remember, I stopped with a short discussion of curves. What we had is a discussion of what happens if we reparameterize a curve. So I could have a curve gamma depending on t, and now I may define another parameterization of the curve. So formally it's a different curve, but it's a reparameterization in the sense that I could write gamma tilde of t tilde as gamma of t tilde. So that's what it means that gamma tilde is a reparameterization of gamma, namely that I can express it in terms of gamma just by changing the parameter, where t is a function. So t tilde is a function. So I somehow say which t belongs to which t tilde, which with certain properties, for example, that it's monotonically increasing always. Now I said that there is a claim, namely that the length of a curve doesn't change if we reparameterize it. So that was the claim in this particular case. And I think I also said that we are going to prove that claim now in case you wish to do so, or in case you wish me to do so. So we make a small poll. It's a very short proof. It will take maybe 5 minutes. Who wishes that I do that proof? Okay, so it seems there. Okay. Yeah, let me not wait for longer. The result seems to be clear. I think there are at least 3 times more people who wish to see the proof, so let me briefly do it. So the proof of that claim depends first on an observation, namely how the direction vector of the curve changes with the move to a reparameterized curve. So let's look at the direction vector of the gamma tilde curve. And as always, we have done that a lot at the beginning of the lecture. We look at a vector, or we study a vector by asking ourselves how it acts on a function. So we just let this direction vector act on an arbitrary function f. And then you know that by definition, what this means, so I should here write really d to the dt tilde, is that we just evaluate the function at the points where the curve passes. And now I directly write this expression for the reparameterized curve that I gave above. So in principle, this is just gamma tilde t tilde. And I take the derivative at a certain point. But let me now not indicate the point, because of course I can take the derivative everywhere along the curve. Now, this expression I just evaluate using the chain rule. So I first say that I take the derivative of f of gamma of t and evaluate that at the point t, that of course itself depends on t tilde. And then I take the inner derivative. The inner derivative is d to the d tilde of t, of this function t that reparameterizes the curve. So that was the function that I mentioned here. Okay, so I should have said is a function. from, actually it takes the old curve interval, or the tilde one, to the AB one, which is the interval of the original curve. I introduced these intervals last time, so this is just and the parameter range of the tilde curve, and that's the thing on the right-hand side here, is the parameter interval of the original curve gamma. So that's just a chain rule, and let me here put that into brackets just to make clear that this derivative to t tilde now only acts on the function t. But now I can just look at this expression and observe that this expression is just, again, a statement that I can write in terms of a velocity vector, of the direction vector of the curve gamma itself. So it's actually just this. And maybe I should really here write, not, it's evaluated at t of t tilde applied to f. So that's just the same step as the one we did at the beginning. And then I just still multiply with this factor that we determined, which was the inner derivative. So that's the first observation. If we reparameterize a curve, then the velocity vectors are just rescaled by such a factor, which is essentially the derivative of t. And now you see why it's actually important that we assumed that this derivative is always positive, because if it was not, we would somewhere have a zero direction vector and the curve could even go back and so on. And that would make our lives more difficult, particularly when we integrate, as we do now. So let's now calculate the length of the curve. And you probably remember the formula from last time. It's just integrating over the metric applied to the direction vector in both arguments. So that's how this looks like. And then the parameter is t for that original curve. Now what I can do is to just reparameterize the integral. So that's something you know from analysis. This is even high school analysis, actually. I mean, in case you had integrals in the high school, if you have an integration of a function, then you can also write it in terms of a different parameter. So here we now say, instead of writing the integral in terms of t, we write it in terms of t tilde. So we express all the t's in terms of t tilde, and the t's now appear, of course, in these direction vectors. So we do that. That's the first thing we have to do, and we reparameterize an integral. But then we also have a factor that we have to add, which is dt to the d tilde times d tilde. It's this Kobe determinant in general, but that's something you know from analysis. This has nothing to do a priori with the derivation I did above, but now we of course see that it's the same factor. So this thing here is exactly the same as that. I just used a slightly different notation by moving the t here up on the fraction bar. So what I can do is to just say, oh, I distribute this thing to these two terms. And of course, if I take this term here, this fraction or this derivative into the square root, it becomes a square, and I can put one in front of this v and the other one in front of this v here. So I could equally write this expression without this factor here, but instead having this factor appearing here and here. But if you look what that is, if I put the factor next to such a term, then I have just, again, the velocity vector without the factor for the tilde curve. So in other words, I just get here, of course, the function g is the same, but now I have the velocity for the tilde curve. Okay, I think that was a relatively easy calculation, but now we are done because this is, again, by definition, just the length of a curve. Okay, that was kind of a warm-up for today's lecture, but that certainly proves now the claim that we made at the beginning. Okay, Are there any questions about that? Or I remember I didn't have time last time to take questions at the end. I'm sorry to say that it will again be the same today, and actually for the same reason. We still have an evaluation committee at ETH. They are here for the whole week. I mean, here virtually, and they want to talk again to me. And this will actually happen right after the lecture. So unfortunately, I have to leave a bit earlier, and we will again work through the break for that reason. So this, I hope, will be the last time in this mode. So at least next week, we will again have usual breaks, and therefore also more time for questions during the breaks. But of course, feel free to ask your questions just right now or during the lecture. So you can, of course, as always, interrupt me at any time. And I'm very happy to hear from you if you think that something should be done or re-explained or explained slower, or also if I should skip over certain things that you already know. If there are no questions, I will just continue with the next small section, which I think already mentioned earlier, which are the geodesics. I think I informally already talked about them, but now comes the formal definition, a curve gamma. And now actually, I really think of a curve segment in the sense that the curve has a well-defined starting and end point for parameter value A and B. This was actually already the case before when we talked about lengths. So if a curve is a stationary point of the function, of the length function, so you see the length function takes as input the whole curve. So the curve is just now an input to a function. And if you talk about the stationary point, what we mean is that if we vary the function, so if we vary the length for different curves, just put that in different arguments, and we get a derivative of 0. So if it doesn't change, if we slightly change the curve, then this is by definition a stationary point. And this could correspond to a maximum length, a minimum length, or even just another point where I kind of have something where for the moment the derivative is 0. So you know that even for, of course, curves of a real number, I can have this shape that it becomes flat and then raises again. So that would also be a stationary point. But generally, we will actually have either maximum or minimum lengths. And actually in GR, we will most of the time talk about maximum lengths in terms of proper time. But I will come to that still today, I guess. Oh, actually, I didn't finish the sentence. This thing is called a geodesic. So geodesic is just a special curve with this property that it has kind of extremal lengths in this particular sense. Now there's a claim I can evaluate this criterion. So I can ask myself, how could I, in coordinates, describe that a curve is a geodesic? And so if I do that in coordinates, I find that the necessary equation that needs to be satisfied looks like this. Where these are the Christoffel symbols. So, remember, the Christoffel symbols are the gamma symbols of a general parallel transport in the case where the parallel transport or the whole affine connection is the one induced by a metric. The proof of that will actually be something you can do in the exercises. It's essentially just writing this in terms, or thinking of this as a Lagrangian, or I mean, if you look at this interval that defines the length, then you can think of this as a Lagrange function, and then you use the Euler-Lagrange equations to determine the extremal points of that L. So essentially, you solve the Euler-Lagrange equation for L being that particular function here, the square root. I mean, L, not that L, but the Lagrangian being that square root. And then what you get, what the Euler-Lagrange functions tell you, if you rephrase then, is that this expression here must hold. Of course, that's all relative to a coordinate system. So to really resolve something, you need to assume a coordinate system and express the coordinates of the curve and so on. So let me just indicate this proof in the exercises. But one thing you should already observe now is that this is an expression you have actually already seen before, but in a different context. Namely, I think it's exactly a week ago. So let me briefly jump to the notes a week ago. Here they are. So you see, this is exactly that expression here that we wrote down a week ago. So what did we do there? So there we looked at the parallel transport and also straight lines. So we found that a straight line, a curve gamma is straight if it satisfies this condition. So now we have made an interesting observation, namely the same condition that characterizes straight lines also characterizes geodesics. In other words, a geodesic is a straight line. So now you could say, okay, that's obvious. I mean, we know that if we walk straight, this is the shortest path. But the point is that the notion of a straight line is something that we could introduce without even talking about the metric. So a straight line is defined whenever we have a so-called affine connection or a parallel transport. And of course, it was defined by just taking a gyroscope and following it. So it's physically, you could think of this something connected to how gyroscopes keep their direction. Whereas geodesics, they have to do with the metric, because this length here involves the metric. So it's something you would really measure things. You would take like a meter stick with you and measure how long your path is. So it's a completely different experiment. One you do with a meter stick and the other one with a gyroscope. And they're also mathematically different structures. One is the metric and the other is the affine connection. And so a priori, they're completely different concepts. However, what we did is to say, when we have a metric on a manifold, then the natural connection is the so-called Levi-Civita connection, which is the one that is characterized by saying that, I mean, remember, I just write this here, the characterization of Levi-Civita was to say that if we parallelly transport the metric, then it should remain the same. So in other words, the derivative is zero of the parallel transport. Now what we found here is that whenever we make this connection, so if we say that we look at the particular parallel transport that is induced by the metric in that way, then we also at the same time have a connection between geodesics and straight lines. And actually we could have done it in the other way around. We could have said, let's just take a notion of parallel transport and therefore of straight lines, and let's look at a notion of metric. And let's now require that geodesics are straight lines. So we could just have imposed that instead of this. And then we would actually also have found the same connection, would have found that Christoffel symbols are the ones given that arise from this condition. So this is in a way an equivalent statement. In other words, to summarize, instead of saying we require this and therefore say what our parallel transport is, how it's induced by metric, we could have required that straight lines are geodesics.
There is one short question about what do you mean formally by stationary point of the length?
Yes. So what I mean is that if you, okay, let me write that. So stationary point, I mean, the point is now a curve. That's maybe the confusing thing. That the point is an argument to this function L. And therefore, it's a point in the sense of being one point of this function. And now what I mean is that if I change, I mean, it's sometimes written like this delta of this gamma, or let me write it in a different, let me actually fully write write it out completely. If I look at an arbitrary curve, so if I vary the curve, I have some gamma that I vary with some, let's say, parameter little, let me put some small parameter epsilon or so. I don't use delta because the delta, of course, too often. And I define this curve as being the curve gamma plus epsilon times something else. So maybe some other curve. Maybe that's not a good notation. Let me first, okay, I'm sorry, I don't want to here immediately write the coordinate thing. So what I could do is to say, let's take the curve gamma, and here I put the delta and put some delta gamma. So this is a new curve that slightly varies from gamma. And now the point is that to first order, that should be the same as the original curve. So maybe the problem is that we haven't introduced this notation to vary with or to talk about variations of curves really well. How should I do it? Okay. Let me fully do it, because otherwise it's just confusing. So if we have a curve gamma, we can of course express the curve in terms of coordinates. So I have a curve gamma, and then the coordinates are gamma I. Now, the curve is of course defined for any value of the parameter. So let's assume that the parameter is, what did we take before? Something like, let's take t. So we have this curve gamma it. So these are the curve parameters. Now let's look at another assignment of parameters, which you could think of as another curve. So let's say curve alpha I. So it just assigns other parameters. Now I can define a new curve. Let's say gamma with a small, here I put now this epsilon I had before. So this is not an index. Maybe I put the epsilon somewhere else. Gamma epsilon here. And this curve should be defined by coordinates by just saying it's the original curve plus epsilon times this deviation. So that's now a new curve, which is defined in terms of coordinates. Now, of course, for gamma, for epsilon equals 0, is just the original curve for all values of t. But if I have positive values of epsilon, it varies a bit. And now the requirement is that if I look at this variation, so if I look at the variation of the length of the curve of this whole family of curves parameterized by epsilon, then this should be 0. So the picture, maybe the picture is clearer than what I wrote here formally. Picture would be the following. I have this curve gamma, and then the curve gamma epsilon is one that is a bit, maybe sometimes you could even agree with it. So this is gamma epsilon. And of course, the alpha that I defined above is just the difference between the two curves times epsilon. And now you look at all variations of that type. So this should be true now for all ways alpha, how I vary the curve. Okay, so it was a bit maybe an overkill to do it like that, but I hope it certainly clarifies. I mean, it certainly gives a formal criterion on what is meant by stationary point. So if this holds for all possible ways how you can vary the curve. Okay.
And there's another question.
Yes.
About, since G is only assumed to be non-degenerate, what would happen if, I don't know, G is negative? Would then the length of the curve be complex?
Yes, that's a a very good question. Indeed, I mean, that would be a problem for my definition, because you see, when I put here into the definition the square root of g, and if g is negative, then indeed I get something complex. So actually, what we will do is we will only look at the length of curve. I mean, okay, we can do two things. So normally we will only look at the length of so-called time-like curves. And I will just, maybe I will define in a minute what this is. Or let me do it now. So that's the definition I anyway was going to make today, a bit later. And then I will answer the question. So a vector V is called, I mean, I think we have probably seen that earlier already in the linear algebra part. Okay. It's called time-like if this G is positive. By the way, that depends on the convention, and it's this, what I'm writing here is only true for the convention where this eta that I introduced last time, the signature of the metric, is 1 minus 1 minus 1 minus 1. If I take the opposite one, which is really a matter of convention, the one which has a minus 1 and then 3 ones, everything just changes the sign of what I'm writing here. It's called like if this G VV is equal to 0, and space like if G VV is negative. Now, the same definition can be applied to curves. So generalization to curves. And this I just say in words, but it's really obvious. A curve is called time-like if its direction vectors are always time-like. And the same for space-like and light-like. Of course, it could in principle be that it changes, and then it's neither of them. So a curve that is for a certain time time-like, and then later suddenly becomes space-like, doesn't have a name. It's neither space-like nor time-like. Now the point is, to come back to your question, if as long as we measure the length of a time-like curve, we have no problem, because by definition this is always positive. For a light-like, by definition, the length is always 0, and for a space-like, we have this problem. So the convention is that, I mean, first of all, the convention that I chose here is such that we have the positive case in most situations that are of interest to us, because in most situations we will only be interested in time-like curves. Time-like curves correspond to the actual real trajectory to the world line of particles. There is nothing in the universe that moves on a space-like curve. So this thing simply doesn't exist as a physical object. So that's why the problem doesn't really occur that often. Of course, we can still draw mathematically a space-like curve. For example, if we want to somehow define spatial distances, but this doesn't correspond to a physical object. If we nevertheless do it, then we usually just consider essentially the negative of that. So we just treat it with a minus the metric for defining the length. And this is then essentially the spatial length. But as I said, the physically relevant thing will mostly be that, because we are mostly interested in world lines of actual particles, which are either time-like or light-like. Okay. Are there other questions? Okay. So, yes?
How did you define DI order when you were explaining a stationary point?
DI.
Yeah, the addition that is multiplied by epsilon. Yeah.
Oh, this was an alpha I. So this is just an arbitrary function. So you can see it like the coordinate of a curve is a function of t. And now to vary that coordinate, I define another function of t. So alpha I of t is just the real number for any t. And of course, you would assume it's a smooth function or some integrable function and so on. I didn't specify that. Just think of alpha I of t as some nicely behaved function of t. Does this answer your question?
Yeah, so epsilon is a small variation, but on alpha we don't have such thing. On alpha is a curve itself.
Yeah, so you should think of alpha, like for example, you could say, I want to just see how the curve, how the length of the curve changes if it has, for example, such a bump here. So what I would do is to have a function alpha, which is, for example, 0 here, and then it becomes maybe 1 here slowly, and then goes back to 0. So I only add stuff in the middle. Now, how much I add, if I say it's 1 here, this is of course not infinitesimally small. So I want to see if I only make a very small bump, what happens. So I multiply this. So this essentially gives me the direction in which I want to deviate, and this tells me how much I want to do that.
Epsilon is the scalar just to make it smaller.
Yes, right. Because at the end I need to take a derivative. And so I want, maybe I should say, of course, this is evaluated at epsilon equal to 0 at the end. So I want to see how does it vary if epsilon is very small. Yes, that's right.
Thank you.
You're welcome. Okay, thanks a lot for these questions. Now, yeah, we have already now defined geodesics, and for the moment, I don't want to say more about geodesics, except for the fact that you probably already know that the world lines of particles that are not subject to force, that don't feel any forces at all. And now I'm hesitating a bit because I'm already assuming that I'm not treating gravitation as a force. So, okay, maybe you should first say that. So remember in the first course, we said that we can look at this equivalence principle and so on. And already there, it was probably clear that gravitation shouldn't be treated as a force, in the sense that we don't have anything to compare it with. What is this? The idea is more that the space-time is curved, and whatever is the straight line here is corresponds to a particle that is not subject to any forces like electromagnetic forces and so on. But of course, what we call a straight line depends on the metric. So the gravitation already comes in is already incorporated in a way. So when we talk about straight lines, that concept already depends on the gravitational field in a way. Now you could ask, why don't we actually say, no, there is something that it would really be straight, and then the gravitation is a force that deviates that a bit. But that would be a completely wrong view, because then we would have to define something that is there, a space-time essentially that is there in which there is no gravitation, and then compare that to the one where there is this gravitational force. But that's not the view we should take in GR. I think the conceptual insight in GR is that there's not such a thing like a space that would be there if there was no gravitation. That is at the same, I mean, that is already defined without gravitation. The space is immediately incorporating from the first point on the gravitation itself. So the structure of the space contains that force. And in that sense, we are no longer considering really it as a force. It's just a geometry. So the statement is therefore a particle that is not subject to a force. Now, force in that sense, restricted to non-gravitational effects, is a straight line. So that's the geometric meaning or the physical meaning of geodesics. The geometric meaning is that it's just the shortest line. Okay, now I would like to move on with a chapter that brings us already a bit even closer to physics, which is geodesic deviation. So what I just said before tells you that you would, and that's also what the equivalence principle tells you, you cannot actually measure gravitational force by just looking at one particle. So suppose there was only one particle in the universe. And now this particle just moves. And now the naive view I mean, this is a bit repeating what I said, but maybe putting a different focus. So the knife would be the amount by which the movement of these particles deviates from a straight line tells you how strong the gravitational force is. But as I explained before, this doesn't work because you would already need a straight line to compare it with. But the view is rather, no, the particle by definition goes along a straight line because it's the only thing in the universe, so it's certainly not subject to any forces. So it just defines what a straight line is, and we cannot compare it to anything else. Now, that's indeed also what the equivalence principle tells us, because if we would just fly with the particle, we wouldn't see any gravitational effect. That's it would just behave as we are far away from any gravitational source. So the question is now, what are really the effects of gravitation? Because clearly there is, at the end, we talk about gravitation. It's something we can measure. And what we really do measure is not the effect on one particle, but somehow the effect that gravitation has on several particles. So for example, if I have two particles, and if there is a real gravitational field, for example, I have one particle a bit higher up and one further down, then we know that the gravitational, now in the traditional sense, we would say, the gravitational force on the upper particle is a bit weaker than on the lower one. So therefore, it will be a bit less accelerated, the top one. And so if I just measure the distance between the two, then this distance will slowly increase over time. They will both fall, but this will fall a bit slower than the other one. So we can measure this distance and how it increases. And that's really an effect that is directly measurable. So that's a real effect of gravitational forces. Now, of course, in the modern view, in the view that is introduced in GR, we would say both go along straight lines, but because there is a curvature of space-time, the distance between the two may still increase. And that's what we want to study in this small section on geodesic deviation. So maybe after I explained everything here, we may come back to that explanation, and then you probably understand better what I meant. So I start by drawing this usual picture of having the real space-time somewhere, and then we have a coordinate representation. And let's now do that experiment that I just described. And the experiment is, of course, one that takes place in real space-time. So let's suppose we have a particle and we just let it fall freely. So it goes along a certain world line, and we call this world line gamma 0. Now let's suppose we have another particle, which is maybe at the beginning quite close to the blue one. Of course, it shouldn't be identical, but let's suppose it has the same, almost the same velocity and almost the same initial position, and it moves, but maybe like in this example that I just described, and now for some reason it made a straight line. So like in the example I just described of the two particles in gravitational Earth field, with time their distance may increase. Okay, this is maybe now when the distance increases a lot with time. So maybe the picture should not mislead you by thinking that at the beginning they're identical. They're already a bit different, but the difference becomes larger. But both of them are geodesics. Now let's represent this experiment in a chart. So a chart is, of course, depends on the choice of a coordinate system. Now, in the choice of a coordinate system, I really have a choice, and I could choose the coordinate system in such a way that the coordinate line, which I call t for time, is such that it's just perfectly aligned with the trajectory of the world line of the particle. So I choose the coordinates in such a way that the chart representation x of gamma 0 of this curve is just this y, or this vertical axis, and I do the same actually for this other thing. So I call the curve of the second particle gamma delta s. Why I call it like that will probably become clearer a bit later. So I could also choose the coordinate system in such a way that here the coordinate line of the particle is like this. It's also a straight line upwards. And such that, okay, the delta S should indicate the distance between the two in some way in these coordinates. So this is delta S. And of course, I have some spatial component here, which I call S. So this, imagine that the two particles are initially spatially at different locations, and the distance, like the spatial vector from here to here between the two, up to down, is oriented such that it corresponds to this coordinate line. Now it's relatively easy to see that I can always choose a coordinate system in that way. I mean, if I have no other constraints, I can say, let's choose this coordinate line being that geodesic and this coordinate line being the other geodesic. I cannot do that with arbitrarily many. I cannot say I also have somehow geodesics always in this direction. But as long as I have just two coordinates lines which never intersect, I can choose them however I like. This you can easily verify by just thinking how much degrees of freedom you have in these choices of coordinate systems. Okay. Now you see in the coordinate system, but this is just a coordinate system, the particles look as if they are always parallel. But that, of course, doesn't mean that the distance between these two doesn't somehow increase, because that's just in the coordinates. And you see the real thing is here, and they may become more distant to each other. But let's now analyze that. So these are all pictures, and at the end we need to, of course, really see what you can say firmly about these things. So the first thing I would like to do is to essentially express the distance as a vector between the two. So you could imagine that this would now be one of the rare examples indeed of a space-like curve. So I could think that I just connect these two particles here. Now, if I have a curve that is very short, that's what this delta should indicate. So I do this experiment with particles which are quite close. Then I can always characterize the curve almost completely by the direction vector of the curve. Because, I mean, if the curve is really, I mean, we have already assumed that everything is differentiable. So if I'm in a small enough area around the point, then the curve almost looks straight. And so the assumption is that delta S is so small that this connection between the two is almost like it's very short. It's just so short that everything can be approximated to first order. Then I could think of this curve essentially, or of this connection curve, of this orange thing, just as a vector. So I always said that when we introduce charts, that the idea of charts is somehow that locally things look like a flat space. And talking about the tangent space really means that we are very close to things. So in a way, as long as we are in a small enough region, instead of talking about curves, I could just talk about vectors. And that's the idea here. So I'll introduce a vector, which is time dependent. So this vector, let's think at any time t, I have such a curve which somehow connects the two world lines, the blue and the green one. And this vector is essentially the green thing, so the orange thing. So maybe I write it even in orange here, e to the ds. Okay, now I'll like this. So what do I mean by this? So of course, the vector pointing in this direction is by definition, by the choice of the coordinate system, p to the ds. And remember, a vector in the direction of the coordinate, we wrote like that. So what I'm saying is essentially that I'm expressing this curve here by this vector delta. And this thing just means that I'm doing that at any point here. So the zero means I'm staying here on the blue line. So I essentially have vectors of this type. So these are the vectors. These are the S vectors, if you like. And the t is the second coordinate. So that's the thing that goes upwards, and I may have more coordinates which I just don't consider. So let's suppose all the other coordinates are 0. Okay, that's what I wanted to define. So that's the thing we are somehow interested in. It's you can think of S really as the vector connecting the two curves. So when I have these 2 points falling down, you could imagine there's a small vector connecting them. I mean, connecting, not physically holding them tight, but just the vector connecting them. And now we are interested in how this vector changes as things move down. Now, of course, it looks like this vector never changes. It's always this orange vector. But of course, if I draw the picture again in the real thing, then you see these orange things become longer and longer in this figure. So it's not a good indication, again, to say, oh, this thing doesn't change because it's always d to the ds. That's just an artifact of the choice of coordinates. But how does it change? So we could now define another vector, which we call v of t, which we just define as how the vector changes. And of course, what we want is to look at that change in a coordinate independent thing. So we somehow want to say how, as we move in this direction, as we move up in time, how does the S change? So it's first this and that and so on. And we call that V for velocity. Why did I call it V? Imagine again the 2 points that fall in the Earth's gravitational field. The V would be the relative velocity of this point relative to that one. So S is the relative vector, it's the vector connecting them, and V is the change of that vector, and therefore the relative velocity. In the very same way, I could also define an acceleration, which I call capital A here, which is just defined in how the velocity changes as I move up in time. These are the statements. And so the A, so these are now all objects that are defined at the end. I mean, this thing is first coordinate dependent because I need to say in which direction I really want to compare the things. But once I've defined this, so once I've fixed the direction in which I want to compare the distance, this essentially tells me which direction is space. Then all these derived objects are independent of coordinates. But they, of course, if this A is non-zero, this tells me that apparently there is really a change in this vector. So this tells me these things will acquire a velocity vector that, for example, increases all the time. So in other words, this A of t is really can be interpreted as if you were an observer sitting on the blue curve, what would you say about the acceleration of the green thing? And both are free falling. But of course, from your viewpoint, you would say, oh, yes, it's free falling, but still it's accelerating away from me. And that we want to determine. Okay, so that was maybe the difficult part because this required some connection to physics. Now the rest is pure, is in a way just pure calculation. So let's analyze that. Let's just calculate A. So first of all, we assume, like always in space-time physics, or at least in GR, we assume that space-time is torsion-free. So in other words, T, remember T is a 1-2 tensor, and I can put in elements. I can, for example, feed it in the second and the third argument with these basis vectors of the coordinate chart. And of course, if T is 0, it's in particular also 0 in this case, if I insert these elements. And now if you remember the definition of the torsion, then this just implies that d to the dt of d to the ds minus d to the ds of d to the dt is equal to 0. So the torsion also has a Lie bracket, but you probably know in the meantime that the Lie bracket of coordinate-induced basis vectors always vanishes. Okay. Now look, I mean, essentially what we have determined now is that this derivative is equal to that derivative, and that will be useful. Now, to analyze A, we want to evaluate this. Let's look at an arbitrary component of that. So remember that if we want to know a component of a vector, we just put the dxi in front of it. So that's just the i's component of A. Maybe I'll write that as well, just to remind you. That's, of course, again, now a basis-dependent statement, but the A itself, the vector, is not basis-dependent. But of course, if the observer, the blue one, the one on the blue curve, wants to say, what is really the vector A? He has to use a basis. And with respect to that basis, we now express A. Now, what is it? So I'll just put in the definition of A, which is, in a way, the second covariant derivative of this connection vector ES. So far, I just used these things here all together. Now, when you look at this, I can, without any harm, add another term. So I'll just copy this again. Or, okay, let me just immediately do it. I can just add something. Namely, I can add the thing with the opposite order in the first argument. Or let me subtract it. That's even a better idea than adding it. So let me subtract something, namely the oh no. Okay. I think I'll nevertheless do it in 2 steps, because otherwise it will get confusing. So let me first do a step where I simply use the rule that we just wrote down, namely that this thing is identical to that thing here. So I can therefore write this as dxi, and then the first derivative I don't change, but the second one I exchange the direction of the derivative with the vector that I derive. And now I do this trick that I wanted to do. I'll just add something else, namely something that, or subtract something else, namely the derivative where I do the opposite order here. But I justify that I can add it by saying that this is anyway 0, or more precisely, actually, this thing here on the right-hand side, the last thing is already 0 by itself. So this is 0. Why is it 0? The reason is that this is the how the direction changes of the blue curve. So if you look at this, e to the dt is the direction vector of the blue curve. And if I now look at this derivative, this is the change of the direction vector, but the change of the direction vector of a straight curve disappears. And because we assume that the blue curve is a geodesic, and therefore straight, this thing has to disappear. So I can add or subtract it without any harm. But why did I add it or subtract it? The reason is that now I have a very nice expression, because if you look at this, I have once this derivative and once the one in the opposite order. That should remind you of something, namely of, and I will do that immediately like this, of the curvature. The curvature is exactly defined like this. And again, there would be a Lie bracket which disappears for the same reason why the Lie bracket above disappeared, because we have a coordinate-induced basis. So it's the following, just by definition. Go there and look at the definition of R, and it just matches exactly this thing. Okay. So now we have found something quite interesting. We have found that apparently the acceleration somehow depends on the curvature. So the way these two objects, when they fall down, the amount by which that one accelerates relative to the upper one is directly determined by a quantity we already know well, namely R, the R tensor. Maybe I could write it in a different way, again in a coordinate. I mean, this was now all coordinate dependent to do the calculation. But once we have achieved that, because all the quantities that we have inserted are somehow, I mean, let's say the reason why we actually put here a covariant derivative is exactly to make these things, all these definitions independent of the choice of the coordinate system. So the only thing that really depended on it was what was the direction of the blue curve. But let's just say, so let us call the direction of the blue curve d to the dt, let's call that u. So instead of just writing d to the dt, I can just say I call the direction u. And of course, for the calculation, I chose this coordinate system where this matches. But now this allows us to write things in a nicer way. So now AI is given as essentially d. Okay, maybe I'll write it down again. By definition, it's now the derivative in the direction u. So everywhere where I have a d to the dt is now a u of s of this s vector. And what we calculated is that this is really just the curvature. And now, of course, wherever there is a dt, I now put the u, and the s is the connection vector between the two. And I can even write this in components. I, j, m, n, u, j, u, m, s, n. And that's our result so far. So let me again discuss what it tells us. So what we found is that the A vector, the acceleration of one particle with respect to the other, is given by knowing u. But what is u? U is kind of the direction of the blue particle. And of course, initially, I could assume they had almost the same direction. But so u is the initial vector, and the s is the initial connection vector. So in other words, I can now I have a general formula for doing that. I have a particle flying here with a direction vector u. I have another particle in a distance s. So the connection vector is s. And now the formula tells me how will the second particle accelerate away from the first. And the insight is, if the curvature was 0, there would, of course, be no acceleration, because two things that move in straight lines, or according to geodesics, two particles which are not subject to force, just keep their distance. There's no change. But if there is curvature, then two particles which are both not subject to any forces, non-gravitational forces, still may start to accelerate away from each other, or of course also towards each other, depending on the sign of this R component that comes in here. So we have therefore another interpretation of the curvature. So far, I always told you an interpretation which had to do somehow with gyroscopes and so on. Now we have an interpretation of curvature in terms of how a collection of particles, now you can apply to a whole collection, how they start to diverge or how they start to converge towards each other. Okay, I think that finishes another section. Do you have any questions about that part?
Sorry, what if the direction of the blue line was not a straight line, which you could say that part is equal to 0 that you subtracted?
Oh, so if the blue one is not a straight line, that's your question. So,
yes, basically, what if you couldn't put that equal to 0?
Yes, so you said it's the following. If I start, so the whole statement is only true if the blue and the green ones are both geodesics. So that's just an assumption. I cannot So this formula doesn't hold if there are additional forces. But geodesic means there is no additional force. There's only gravity. And so therefore, I already know they are geodesics. Now, the claim is that whenever I have two geodesics, I can find the coordinate system such that it looks like this. And essentially, you can just construct the coordinate system like that. And you just say, there is, of course, this blue line is somehow defined, and you just define this to be one of the coordinates. I mean, you just essentially say that by definition, whatever you call the t coordinate, I mean, you start, of course, here, but you say that any point here along this curve, by definition, has always the same s, namely s equal to 0. That's just what you define. And then you say that the only component that changes is the t1. And you do the same for, let's say, s equal delta s, and go along that one. And that just defines two lines. And yes, I mean, essentially what I'm saying is that you construct the coordinate system in that way. So the question is, do I have enough degrees of freedom to choose the coordinate system in that way? And that's actually a general statement. You can always take two arbitrary lines. I mean, let's suppose I take the Earth's surface or something. I can take two lines which don't intersect and say that there is a coordinate system according to which one line corresponds to the one where x is 0 and y increases, and the other line is one where x is 1 and y increases. This is always possible. That's something you can easily verify. And that's essentially what went into that. So I just said I choose a coordinate system in which this is the case.
Yes, thank you.
Okay, you're welcome. Thanks for the question. Are there more questions about this? This is maybe really something that is conceptually a bit more difficult to grasp, because this is not a pure calculation. You have really to make this connection to physics. And you have to understand what these things mean. So think about it, and if there are questions coming up later, you can of course also ask me next time.
When you say, wait, is my mic on?
I can hear you. Yes. Hi.
Okay. When you say that you can always find such a coordinate system, you mean like only if they're actually like near enough or something? Like.
Oh yeah. Okay. Yes, I wasn't very careful. Yes, I have to admit that this was a very generous statement. Yes. So the more careful statement would be there is always a small enough delta S for which I can do it. Of course, let's say the physics reason why I didn't say that is that I was thinking really of an experiment you do. Let's say you take two particles and do that. And space-time, like the curvature of space-time, is usually so small compared to the distances we have. So what I mean by that is that if you calculate such a thing with the real curvature of the space-time here and the real u and s vectors of an experiment. So the s vector would really be, let's say, an experiment. Let's say even if I do an experiment with spaceships or so, I may take two spaceships which are maybe a few million kilometers apart from each other. But even then, this million kilometers, if I multiply it with r, will give me an extremely small number. So, formally, it's certainly, I should say, when this is true, you can always do that if S is sufficiently small, but essentially in practice, for all experiments we can do, this is not a concern. By the way, that's something I should always say, because whenever I do something in a chart, we always will assume that, it's always implicit that whatever I'm saying is a priori only true in the chart domain. And you know the chart domain is finite. Or, finite, usually it's bounded. Now, there will be, and this will become relevant next week, there will be interesting cases where suddenly we get really at the edge of a chart, and that is relevant. And this is when we study black holes. So there we will have charts where at the black hole horizon, the chart just ends. And then it's not clear whether I can now find a chart which continues towards the inside of the black hole? The answer will be yes, we can continue it. There's another better chart that covers that as well. But there the question becomes less trivial. But there we are really talking about distances and so on, where this becomes relevant. But thanks for asking the question. That's something I should have explained anyway, because I was just kind of talking a bit loosely about these, let's say, about the window in which this whole thing is valid.
Another question is, what would happen if the geodesics would intersect?
If they intersect, I guess it would, I mean, just for the calculate, or for, I didn't want to do it because it may result in certain difficulties, but I guess as far as I can see, it should actually still work. And what would be problematic? I mean, of course, I would have to look at two charts and so on, because it's not so clear I can find, I mean, what I cannot do is then to find one chart in which this is true, because two coordinate lines never intersect. So the way I proved it would not go would not go through in that way. However, I could probably still somehow analyze it up to the point where they intersect using one chart, and then using another chart after they intersected, and somehow by continuation, by continuous continuation, assuming that everything is continuous, still get that statement. So I suppose, but here I'm not 100% sure that this formula would still apply in that case, and we just would have in the proof to compose different charts. But that's now just a guess. Maybe you can try to verify. I mean, I don't see a reason why it shouldn't, at least not a physical one. Are there more questions? Okay, this is not the case. Then let me come to one last section for today, which is normal coordinates. Now, this is something we already had a section about. You may ask, why are we now again having a section about normal coordinates? But this time, it's normal coordinates for metric manifolds. And last time, we didn't have a metric. So, of course, it's not a different concept. It will be essentially an extension. So remember what I told you last time when we talked about normal coordinates. We said, look, we can look at the point P of the manifold. And then there exists a coordinate system, or more precisely, a chart, such that something nice is true, namely all the gamma symbols disappear. And I said, this is very nice, because if the gamma symbols are all zero, then the covariant derivative is equal to the partial derivative. And we don't have these additional correction terms that are maybe quite cumbersome. In particular, they become cumbersome if you take second derivatives, because then you have to take derivatives of these gamma symbols and so on. But the problem is, and remember this is also true now, that this is something we can only do at one particular point. So we can find a chart where at one desired point, maybe the point where we want to do the calculation, all these gamma symbols disappear, but they will not disappear in other points. Now, we can do the same for the metric. So we can, again, say there is a coordinate system such that, and now there comes kind of a small table. So maybe write here again the connection. So for the connection last time we had this I, J, K at the point P is 0. This will still be true if you take the Levi-Civita connection corresponding to that metric. So in that sense, what I'm now saying about normal coordinates is an extension of what we said before. But now the statement is the following. First of all, we can make sure that the metric has this nice form eta. So remember, eta in terms of a matrix. I shouldn't write things in terms of a matrix, but it's essentially the diagonal matrix. Even put it maybe as in gray or some color. So as a matrix, this would be 1 minus 1 minus 1 minus 1. So that's something we already know, because I told you last time that we can always diagonalize the G tensor. And so, of course, we can just go to a certain point in the manifold and diagonalize it there. So that's nothing new. That's not yet normal coordinates. But we can do something much stronger. What we can do is we can find a coordinate system in which this is true. So the metric has this form. But in addition, it is also true that if we take an arbitrary first derivative of the metric, then it's also zero. By the way, this is now not a covariant derivative. That's a coordinate-dependent statement. Of course, the covariant derivative of the metric is always zero. That was the property of the Levi-Civita connection. But now I'm saying there is a connection in which, as I move away from the point, so if I want to see how does the metric change as I move in a direction k, I mean, not how does the metric change, but how does the components, how do the components of the metric change? Then the answer is to first order. And if I take the first derivative, they don't change. Now, the proof of this is again something that I leave to the exercises. Actually, we have already almost done such a proof. We have actually done it for the thing on the right-hand side for this. And this will be useful as you do that proof. So it's in a way, to some extent, a repetition of the proof here, of course, with some additional elements, because this is a different condition. So we cannot generally go from the right to the left, by the way. But so if the gamma symbols are zero, this doesn't imply that it has this form. It's a stronger form of normal coordinates. And in the future, when I talk about normal coordinates, I will from now on always mean in this stronger sense, in the sense that the metric has this form at a certain point. Now, there are two remarks, and these are remarks that you should really remember. I mean, these are typical questions people get confused about. The first remark is, if I take a second derivative, can it still be, so can I hope to extend that to second derivatives? And the answer is no. There is generally no way you can achieve, or you can find a coordinate system or a chart in which also the second derivatives disappear. And why am I so sure about that? So the answer is that if the second derivative disappears, and by the way, equivalently, I could ask here, what about the first derivative of that? Here we just say the gamma symbols are zero. By the way, the gamma symbols consist of derivatives of that. So this is kind of consistent. If these derivatives are zero, then also the gamma symbols are zero. But if I take the derivative of a gamma symbol, then I get second derivatives of these g's. And so why can they not be zero in general? The reason is that if you think about how the curvature is defined, and now this is one of these formulas I mentioned you should probably try to remember, or at least keep on your short list of things that are very important, then you may remember that the curvature essentially consists of derivatives of these gamma symbols, first derivatives of the gamma symbols, as well as multiplications of gamma symbols. So if the first derivatives of the gamma symbols were all zero, or equivalently, if the second derivatives of the metric were all zero, then necessarily the curvature was also zero. But we know the curvature is a coordinate-independent thing. So if the curvature is a tensor, and if a tensor is non-zero, this means in any chart representation it has non-zero components. So in other words, it cannot be that you find a chart in which a tensor is zero and in another chart it's not. So being zero, for a tensor being zero is a chart-independent statement. So being non-zero is therefore also a chart-independent statement. So we know there is no chart in which the curvature disappears. Therefore, this quantity, the first derivative of this quantity, cannot disappear. So that's something that is really important. Unless, of course, the curvature is zero. And there it's again possible. So if you are in flat space, then you can indeed find normal coordinates which are not only normal at one point, but in a whole, it's actually everywhere. There may be some topological constraints, but essentially you can then extend them.
Could you scroll down a little bit on the right-hand side?
Yes. Okay, now the other, okay, that was a very important remark. Now, of course, the other small remark that I already made, and that I need to write something, is of course in normal coordinates. So in normal coordinates, we always can now replace still this thing by the partial derivative. I mean, that's what you already knew. That was when I said that the gamma symbols disappear, but you cannot do it for second derivatives. So, and now you may ask, why is it not possible for second? Because if it's true for first, I can just apply this again and again replace this symbol by that. And the reason is, of course, or I mean, if you think about it, you will immediately see what the reason is. So when I say that first derivatives have this form, then this is only true at the point. That's what I wanted to point out. So maybe so at the end, I evaluate this at the point P, whatever I derive. And if I take a second derivative, of course, the second derivative does not only depend on the first derivative at that point, but in the whole area, because you need to know how this first derivative changes. But we only know that the first derivative at this point is of this form, not in the whole neighborhood. And that's why you cannot take second derivatives and still say, oh, this is just a partial derivative. Okay. But this will, of course, automatically appear. I mean, it's something you just have to be aware of, but the formalism is chosen anyway in such a way that such mistakes shouldn't happen. Now, I think we are now actually really at the point where I've introduced everything we need to be able to talk about geometry of space-time in physics context. So now I think we are ready to discuss black holes, for example, and that's what we are going to do next week. And yeah, maybe this is also a good point to take, again, questions about the mathematical part that I just discussed, or anything I discussed in the last few weeks, because we will need a lot of these concepts now in this real physics context. And maybe it's good if you now reflect about them. You don't need to ask now, but it's maybe now a good time to again briefly go back and see what are the things we have learned and make sure you're ready for the discussion of now more of real physics, so to speak. If there are no questions right now, let me just start to give you some idea of what now the connection will be to physics. So first of all, as we just discussed normal coordinates, I said that several times when we discuss normal coordinates in the context of connections. Normal coordinates are essentially the coordinates we are usually using when we do physics, when you did physics before doing GR. And for example, when you learned about the Maxwell equations, then you usually always probably use a chart implicitly, which has the property that in the context now in which we define things, it would correspond to normal coordinates. I mean, not always, you may go to spherical ones, but essentially it would be easy always to go back to normal coordinates. And maybe the statement that I still want to make now is that this is more an observation, this is not a mathematical claim, but the laws in normal coordinates physics laws look the way we are used to from non-GR physics. Okay. That's a very vague claim, but maybe the best, instead of making just a claim and then leave you confused, let me make an example. So I guess most of you have already learned electrodynamics. And in electrodynamics, one can write the Maxwell equations in a very nice form. And maybe you have also seen that we can introduce the electromagnetic field tensor, which just summarizes in a nice way, and of course in a way which also has nice transformation properties, the electric field and the magnetic field. And it looks like this. Just write it down here. I think it's good. If you haven't seen it, then just think of it as an object that somehow combines the information of both fields, of the E field and the B field, in one mathematical object. So that's this thing. Now, this is not an arbitrary way, of course, of summarizing this information. It also turns out if you now want to write down the Maxwell equations, for example, the homogeneous ones. So you know the homogeneous Maxwell equation. So usually the first way you learn, the first form in which you learn them is usually that people tell you the divergence of the magnetic field is zero, and the rotation of the electric field plus I think the time derivative of the magnetic field is also zero. But a much more compact way of phrasing these equations, and you can easily verify that it's equivalent to what to the normal homogeneous ones, is to say, take this field tensor and take the derivative in the direction k, and then take the antisymmetric summation. So this means you take fijk and then minus fjik, and so with all permutations, and you just say this should be zero. So this is now true in normal coordinates. So that's now essentially the claim I'm making. So that's something you just probably have seen, or you can, I mean, if you haven't seen it, it's really just equivalent to write that the divergence of P is zero and the rotation of E and so on is also zero. So that's a way to write it. That's the classical pre-GR way of writing it. And the point is now in normal coordinates, even in GR, I mean, in GR we generally have new physics. It's not clear how something we learned, how it behaves in flat space-time now behaves in a curved space-time. But essentially this way claim I'm making is that it's still usually true in normal coordinates. But now, of course, if something is true in normal coordinates, we know it's not generally true. I cannot say this expression here is also valid in another coordinate system or in another chart. However, and what I can, of course, say is that if this is true in normal coordinates, then it's also true if I write here a semicolon. A semicolon here stands for the covariant derivative. And of course, we know, and this is what I said before, here you'll see it, that we can replace the covariant derivative by a normal partial derivative. So the comma can be replaced by a semicolon in this notation, and then it's still true. But this is now a coordinate independent statement. So once I have this statement, I can say, okay, that's a statement I somehow derived or did experiments and found, but I wrote it down in a coordinate independent way. So now I can express it in whatever coordinates I want. This is a physics statement, and this is just a statement that depends on our conception of how we do coordinates. Now, I should maybe add that in this particular case, by certain symmetries, it turns out that this is actually, again, equal to that. But that's just kind of an independent effect. But for the purpose of the example, think of this is really the way to phrase the law at the end. Of course, it's equivalent to that in normal coordinates, but this is coordinate independent. And of course, the underlying assumption is physics doesn't care about the coordinates we choose. That's a very reasonable assumption. And so it's much more reasonable to take this as the law than to take this as the law. And that's usually what turns out to be the right choice in GR. There are much simpler examples. I mean, this was now from electrodynamics. We can also just go to classical mechanics. And for example, I mean, here we have already seen it more or less. We can just say a freely falling particle is, of course, in normal coordinates. Okay, maybe I'll just go again back to what I see in this last script. So we said that generally a geodesic or a straight line is this, but in normal coordinates, of course, the gamma symbols go away. So in normal coordinates, a straight line is just one in which the second derivative of the curve is 0. So it's really just a straight line in the conventional sense. The curve just doesn't bend. And okay, maybe I don't, there's no need now for me to write really something down, but we could, no, let me do, I mean, we could again say, you could do the same procedure as I did for electrodynamics. You could say, we know in classical pre-GR mechanics, and so the world line of a particle without force that is not subject to forces. And again, I take the view, okay, in pre-GR there should be no gravity. So let's look at the particle, for example, in the context of electrodynamics, and I mean there could be an electromagnetic force. But now, if there's really no force, if it's not charged, then it's a straight line. We would say that's the law. Gamma dot I is equal to 0. Now here this double dot is maybe a bit confusing. We could also, if we now use our notation, say that it actually means that V dot, so V is now the direction vector of the curve, is 0. So this just means the direction, and this is again in pre-GR. You could say if you look at the direction vector of the curve and we take the dot, meaning the time derivative, it simply doesn't change. And now the claim is again, this is just true in normal coordinates. But now we cannot directly say that this is also true in general coordinates. So again, we have to somehow rephrase things. And now we have to ask ourselves, how do we rephrase such things in general coordinates? And of course, we have seen what it means to take the dot in our case. So this can still be equivalently written as we take the derivative in the direction of the vector and write this. So this statement is equivalent to that in normal coordinates. But there's a difference between the two statements. This statement, as well as this, so these two statements, they're only valid in normal coordinates. They're coordinate-dependent statements. And maybe I should here write gamma I to really indicate that this is coordinate-dependent. So I take the derivative, because otherwise the derivative is not even generally defined. So I have the i's coordinate. If I take the time derivative of that, doesn't change. That's certainly something that is true in normal coordinates. But if I now want to have a coordinate-independent law, I need to get rid of all the i's. So this is a statement of the same thing. I take the velocity vector of the curve and ask myself, how does it change? And now I can calculate it in normal coordinates, this expression. I see it really corresponds to that. So that's therefore an expression that is really expressing what I want, but it has the property that it became coordinate independent. So you see now that the value of normal coordinates is that we can go into normal coordinates, and there we can ask the questions we are used to ask and also get the answers we are used to get and see how things behave. And they really correspond also to the inertial coordinates that are usually considered. Because of course, normal coordinates, if a particle moves straight, that is free falling. This means that you are also moving straight. The coordinate system is moving straight. So if the coordinate system was accelerated, then in this coordinate system, you would see a straight line as an accelerated one. And these are not normal coordinates because these equations are not true. Okay, this is just to explain to you why we are so much interested in these normal coordinates. And I will next time start by telling you that if we move, the normal coordinates are not unique, by the way. So at the point, I forgot to say that, but if you are at the point, there's not only one set of normal coordinates. Actually, you can still choose an arbitrary direction in space-time. And we will see next time that the different choices of normal coordinates are related by Lorenz transformations. So the Lorenz transformation that you may have learned about in special relativity, if you had courses in special relativity, will reappear, but now as a special case. Namely, the Lorenz transformations are just those transformations if you are in a very particular choice of coordinate system, namely normal coordinates, and look how do coordinates transform from one observer who uses one set of normal coordinates and another observer who uses another set of normal coordinates, or physically speaking, from one observer who uses an inertial system to another set who uses an inertial system in that sense. So it's just a very specific transformation, but of course, in special relativity, it already gets us quite far. But in GR, it would be almost useless because it's only valid at one point. Okay, that's it for today. As I announced, unfortunately, I will not be able to stay today for questions, but I'll ask you to keep them again once more to next week, and there I'll make sure that I'll have time in the break and after the lecture. Okay, goodbye everyone, and hope to see you next week again.